Welcome to the Explainer. Today, we're diving into a microscopic battle that defines literally everything around us. It's a constant, invisible tug-of-war happening inside every single substance you can see, touch, or even breathe.
So here's the game plan. We're going to start by laying out the two sides of this epic conflict. Then we'll see how it defines the three main states of matter, and we'll take a deep dive into what makes liquids so special. After that, we'll even explore a fascinating fourth state, and finally we'll put some real numbers on the energy it takes to change the game.
All right, let's kick things off with a question you've probably wondered about. We all know that water, ice, and steam are the exact same stuff, right? It's all H2O. So why in the world do they act so differently? Well, it all comes down to that invisible battle I was talking about, happening at the molecular level.
Okay, on one side of the rope, we've got kinetic energy. Think of this as the energy of motion. It's tied to temperature, and it makes molecules want to just break free and fly apart. And on the other side, we have intermolecular forces. This is the molecular glue, the attraction that's trying to pull everything together and make it stick. The winner of this fight? Well, that determines everything.
Yep, whoever wins this molecular tug-of-war is what determines if something's a solid, a liquid, or a gas. And this entire idea is wrapped up beautifully in what we call the kinetic molecular theory. It's basically the rulebook that connects the tiny world of molecules to the big world that we actually see and live in.
And this table just lays it all out so clearly. Check it out. For gases, kinetic energy wins, hands down. The molecules are just flying all over the place, far apart. For solids, the intermolecular forces are the undisputed champs, locking all those particles into a tight structure where they can only vibrate. But it's that middle ground, the liquid state, where things get really interesting. It's a balanced struggle, a constant dynamic fight. And that balance is what makes liquids so unique.
So let's zoom in on that balanced struggle. This unique situation, where molecules are still stuck close together but have enough freedom to move around, it gives liquids a whole set of special properties that are a direct result of that constant push and pull.
So, picture this. Inside any liquid, not all molecules have the same amount of energy. Some are zipping around faster than others. And the really high-energy ones right at the surface can actually break free from that intermolecular glue and escape, becoming a vapor. That vapor creates a little bit of pressure right above the liquid, and you guessed it, that's what we call vapor pressure.
Now think about a molecule that's deep inside a liquid. It's being pulled on equally from all sides by its neighbors. But what about a molecule right at the surface? It's got neighbors next to it and below it, but none above it. So it gets pulled inward, creating this super tight layer of molecules on the surface. That's surface tension. It's why water forms those perfect little beads, and why some bugs can literally walk on water. It's wild.
And viscosity? It's really just a fancy word for a liquid's resistance to flow. You know, why does honey pour so much more slowly than water? Well, its molecules are bigger, and the intermolecular forces, that molecular glue, is way stronger. That makes it harder for the layers of liquid to slide past each other, so it has a high viscosity. Simple as that.
Okay, so how do we actually get from a liquid to a gas? Well, when you add heat, you're cranking up the kinetic energy. More and more molecules start escaping, and that vapor pressure starts to climb fast. Now, boiling isn't just stuff evaporating off the top. Boiling is what happens when that internal vapor pressure gets strong enough to literally push back against the air pressure from the outside. At that exact point, bubbles can form everywhere inside the liquid, and boom, you've got a full-on boil.
And when we're talking about strong intermolecular forces, water is in a league of its own. It's the superstar. The reason it has such crazy high surface tension and takes so much energy to boil is because of a super strong type of intermolecular force called hydrogen bonding. It creates this powerful network, like a molecular chain link fence. And check this out. This chart says it all. It perfectly shows the power of those hydrogen bonds. Look at water's surface tension compared to other common liquids like methanol or hexane. It's not even close. It's more than 3 times stronger, all because of that intense inward pull from its powerful bonding network.
Okay, so we've got a clear winner for solids and gases, and a balanced fight for liquids. But what if the battle ends in, I don't know, a truce? Something that's kind of both? Well, that gives us this absolutely fascinating fourth state of matter, liquid crystals.
It's a cool story, actually. They were discovered totally by accident way back in 1888. This scientist noticed that some substances went through this weird, milky, cloudy phase between being a solid and a liquid. They have properties of both states, which makes them incredibly useful, especially once we figured out how to control them back in the 60s.
So what's their secret sauce? Well, they can flow like a liquid, but their molecules stay lined up in an ordered way, like a solid crystal. This amazing dual nature is exactly why they're in the screen of the phone or laptop you might be watching this on. Doctors even use them for medical thermography, where they change color with tiny changes in temperature to help find infections or even tumors.
All right, we've talked about the what, now let's talk about the how much. How much energy does it actually cost to force a winner in this molecular battle and get a substance to change its state? We can put some hard numbers on this.
This number right here,
This is the molar heat of fusion for water. It's the amount of energy you have to pump in to take 1 mole, that's just a specific amount chemists use, of solid ice and turn it into liquid water. Think of it as the energy it costs to just loosen the grip of those intermolecular forces, just enough to let the molecule start sliding around.
But now, look at this number. This is the molar heat of vaporization, the energy you need to boil that same amount of liquid water into steam. See how much higher it is? It's a huge difference. And that's the absolute key takeaway right there. It takes nearly 7 times more energy to boil water than it does to melt it. Why? Because melting just means you have to loosen those bonds. But boiling, you have to completely shatter that molecular glue, totally overcome those forces, and send the molecules flying far, far apart from each other. That takes a massive amount of energy.
And look, this isn't just some abstract concept from a chemistry class. These energy values have enormous, real-world consequences. That plus 6.02 kilojoules per mole to melt ice? Scientists use that exact number to calculate how much energy our planet's glaciers and ice caps are absorbing from global warming, and what that means for sea level rise.
And that leaves us with this final, pretty heavy thought. The very same molecular tug of war, the same energy numbers that we can measure in a lab beaker, are the exact same forces that are reshaping our entire world on a global scale. And understanding the science behind it, that's the crucial first step to understanding what comes next.